Okay, let's get started. This is introduction to the series entitled Optimization in Vector Spaces for Economists. The topic is a survey of optimization methods we economists use when solving various optimization problems. It is a fact of life that in solving optimization problems, we work in various vector spaces. So maybe it is useful to start with an initial definition. A vector space is a space, the elements of which are points in the n-dimension Euclidean space, finite or infinite sequences, or certain types of functions. So when solving various optimization problems in economics, especially in dynamic economics, we work in vector spaces, by which I mean that the solution to such a problem is a sequence, is a vector, or a function, which is an element in a specific vector space. Vector spaces come in various forms, but they have in common that on these elements, on their elements, which are points, sequences, or functions, on these elements, certain mathematical operations can be performed, and these operations abide by certain rules. For us, for economists, this is important because we always work in vector spaces. So I thought it would be useful to prepare the students for the advanced literature in mathematical economics, especially in dynamic economics. So this is a warm-up course to my course Recursive Economic Dynamics, which is built on the Stokely-Lucas textbook Recursive Methods in Economic Dynamics. So by completing this course, the student will be able to use and study advanced literature on dynamic economics, especially the Stokely-Lucas book or the Ljungqvist Sargent book. So let's go back to the third bullet point. So when economists solve optimization problems, we work in various vector spaces, and during this course we will study various methods in vector space optimization. So if we work in a certain type of vector spaces, we use certain methods, but at the end of the day we can unify these various methods. We will see today that there is a common idea underlying these various optimization methods. Our textbook in this course is Optimization by Vector Space Methods. We will perform a close reading of this book, so we will go over this textbook from cover to cover with 17 lectures. The textbook itself has 10 chapters, I guess, if I remember. So the textbook has 10 chapters, but I will add additional exercises, additional problem sets, additional applications from the advanced literature in dynamic economics. So the textbook is not for economists. I guess the textbook is rather for engineers. So these methods come from engineering and physics. So we economists, we will we will make good use of our applications coming from advanced level dynamic economics textbooks. So this is the outline for the lecture series and the agenda for today. This is an introduction to define our topic and to go over some examples. I will show you some examples what it means to define a problem, to describe a problem in a vector space, what it means that our solution is an element in a vector space. I don't plan to work out complete and rigorous solutions. We will go over these examples in the later lectures, in the subsequent lectures. My purpose for today is to give you a comprehensive introduction with advanced examples. So let's do it. But before diving into the examples, let's talk about the prerequisites. The course is supposed to be self-contained. So my intention is to make the entry level to this course to the 0 level. So no serious command of mathematical analysis is required. We will extensively use definitions, concepts, and theories from linear algebra or elementary analysis, but we will discuss these elements in a way to make the students able to make up for deficiencies in these areas. So if we use a concept, if we use a concept, I will give some elementary level definitions. But even if I try to lower the level, the entry level to this course, some background resources might be useful. So here I'd like to encourage the students to use any or both of these introductory texts. One is Sutsketer and Hammond's Mathematics for Economic Analysis, or the other is Osborne's Mathematical Methods for Economic Theory. Both books, both resources are at the same level. They are very easy to digest. They are very easy to use, even for individual learning. And plus, the Osborne book is available online. So if a student has some problems in specific areas such as difference or differential equations, integration, differentiation, set theory, or something, don't be shy and use one or any of these elementary level or introductory level textbooks. We will perform a close reading on Leuenberger's textbook, but our applications, our examples, will come mainly from the Ljungqvist-Sargent book or even the Stokey-Lucas book. Additionally, we will cover measure theory and integration as a topic which Leuenberger only superficially touches, but you will see measure theory and integration is a key topic in stochastic dynamic programming where we work with expectations. So to cover stochastic dynamic programming in recursive economic dynamics, we do need measure theory and integration. So we will pay more attention to this topic than our textbook. And in this regard, our textbook is going to be Barthel's Elements of Integration. You will see measure theory and integration is a small but beautiful topic. So I think you will like this detour from our textbook. As I have just mentioned, optimization in vector spaces is not an exclusive topic for economics. Physics, engineering, they also use optimization optimization methods in vector spaces. This is a branch of applied mathematics. So in economics, we can import these ready-made methods and apply them to economic problems. So in this course, we will learn how to describe and solve various decision problems in economics. This is a hot topic in economics and in engineering too, because the benefit is obvious. If we have the tools to define and solve problems, then we can find optimum solutions by which we can gain higher profits, we can elevate well-being. So the benefit is obvious. By defining, by describing and solving various decision problems and solving them to find the optimum solution, if we implement these solutions in real life, then we can gain higher profits, or we can elevate well-being of a group of people, of a society, or anything. Previously, I mentioned that optimization in vector spaces is a unified approach. I think this is an important aspect of this problem, because the history of a science such as physics or economics is towards finding a unified theory, a unified approach. If we have a look at the histories of sciences, we can see that previously scientists think that they have distinct problems to which they need distinct theories, concepts, methods, and everything. But with time, they realize that the previously distinct problems can be approached with fewer and fewer theories and methods, and in the end, they will find a unified theory, a unified approach. In economics, this unified theory is price theory or capital theory, and the unified method is this vector space optimization. So no matter what decision problem we examine, we can describe the decision problem in a way that we can solve by the use of a certain type of vector space method. This is a real benefit, because we don't need to reinvent the wheel every time. We can use the same methods, the same theories, the same concepts. At the bottom line, we define, in any case, we define a real quantity that measures the outcome of a decision, broadly understood. In economics, in optimal control and dynamic programming, this measure is the value function. So we define a vector space, the points of which are alternative feasible solutions to the problem, and to each possible solution, we assign a value. For instance, in the simplest case, the economic agent has an income to be allocated between two goods according to a preference system. So by which I mean that the agent has a preference system, which we are supposed to maximize. So we are supposed to find a solution to this decision problem, to the allocation of income between two goods. We need to find a solution that maximizes the well-being, the utility of the agent. Strictly speaking, this is a constrained optimization problem because we want to maximize the utility of the agent, but we have a constraint because the agent has an income. So we, in other words, we must spend this income in a way that maximizes the utility of the agent. This is a two-dimension Euclidean space. So we work in a two-dimension Euclidean space because the solution is a vector. The solution is a two-element vector. One element describes the optimum quantity of product X. The other element of the solution vector describes the optimum quantity of product Y. So the vector space, we work in the simple two-dimension Euclidean space. This is the most elementary problem an economist, a student of economics, can solve. A more advanced case is a profit-maximizing firm that is supposed to maximize its profits over a period of time, and the firm is supposed to find an investment plan by which it can maximize its profit. There is a dynamic element in this problem because current production and current profit, they are dependent on the current capital stock. So at first sight, we might think that the firm should maximize its current production to maximize its profit. But as current production is dependent on current capital stock, the firm must pay attention to investment to find an investment plan, and investment takes the sacrifice of current production and current profit. So in the short run, it is true that the firm can maximize its short run or immediate profit by maximizing its output out of current capital stock. But in the long run, in the longer run, the firm, as we will see, the firm is interested in reducing its current output and current profit, because this is the only way by which it can invest, by which it can increase its capital stock. So there is a trade-off between short-run profitability and long-run profitability. So we will study the methods by which, this is operation research in general. So we will study the methods in this course and in recursive economic dynamics too, by which we can find the optimum investment plan for the firm. This is a continuous function. So the investment plan for the firm is a continuous function of time. So to any time, to any t, to any value of t, this continuous function will assign a specific number, a specific positive real number that we will interpret as the capital stock of the firm. So in this case, in this optimization problem, we work in the space of continuous functions, which is another vector space. And in this vector space, we have functions which are interpreted as functions of time, and time might be finite or infinite, depending on whether the problem is a finite problem or infinite problem. So in this common or unified framework, we define a value function that measures and describes the value of alternative decisions. So in the first example, where the agent is supposed to find the optimum allocation of its income, the vector space is a two-dimensional, regular two-dimensional Euclidean space. The alternative decisions are points from the positive quadrant of the Euclidean, two-dimensional Euclidean space. And by the value, this value function, which is simply, we will see, which is simply the utility function of the agent. So by the utility function of the agent, we can assign a value, a utility, to any possible decision, and we can compare the alternative decisions by this value function. And to find the solution to this problem, we need to find that point in the two-dimensional Euclidean space that gives the agent the highest utility. In the second example, the example of the firm, we do the same. We define the value function, which in this case is the discounted sum of future profits. Future profit is dependent on the investment plan of the firm, because this path for the capital stock, it is the variable that determines the profit. So we can find alternative capital path for the firm, and to each alternative capital path we can assign values. By the value function, we can calculate, strictly speaking, we can calculate the profit of any capital path. So we can compare the alternative capital path, and we can find the one which gives the firm the highest profit. I'm saying we can find the one, we can choose the one capital path. This cannot be taken for granted. So usually we want unique solutions, but as we will see in this course and in recursive economic dynamics, we must pay attention to the conditions that ensure that we have a unique solution. Multiple solutions are possible, but we want to describe our problems in a way. We want to find the assumptions, the conditions under which we have a solution. So this is the existence of solutions. So the solution is existent and the solution is unique. So we want to ensure first that solution is existent, and two, solution is unique. This is a different topic. We will cover this topic in this course, and especially in recursive economic dynamics. And after this quick introduction to the problem we study in this course, let's go over the examples. Example 1 is the simplest case an economist or a student of economics can find and can solve. We have an agent called the Homo economicus the economic man who is supposed to allocate its income between two goods, X and Y, in a way that maximizes her utility measured with the utility function. So I know this problem is familiar to you. This is an elementary problem from elementary microeconomics, but for the sake of good order, let's have a look at this problem. Let's solve it. You can see we have the income, which is I. We have the two products, X and Y. And we have the utility function, which is a standard first order homogeneous Cobb-Douglas utility function with alpha in the range 0 and 1. And we will solve this problem with the standard Lagrangian method. It might be familiar to you. We will go over the basic steps of the method in turn. If you want a written source, please use chapter 18 of the Sitzeter-Hammond textbook. So let's solve the problem very quickly. To solve this problem, we need a Lagrangian function, which is a function of our two variables. This is the utility from the decision, and this is the constraint. This is the standard way of writing the Lagrangian, so please have a look at the literature. If alpha is 0.5, A is 1, the price of product X is 10, for Y it is 20, and if income is 10,000, to be concrete, the Lagrangian function is simply this. So this is the function we maximize with the constraint. The necessary conditions comes from differentiating the Lagrangian function with respect to X and Y. This is from elementary analysis. If we have a function which we maximize or minimize, 10 lambda is 0, its first derivative must be 0 with respect to all the variables. Okay, so this is what we do. We differentiate the Lagrangian with respect to X and Y, and we equate the equations with 0. Okay, so now we have two variables, two equations, two variables, X and Y, plus lambda. So we need to find a way to eliminate lambda. Lambda is in both equations, so we can solve the equations to lambda. So here we solve both equations to lambda, and by so doing we can reduce the number of unknowns. So now we have two unknowns without lambda, and from some manipulations it follows that x equals 2 y's. This is a very important result because this equation clarifies the ratio of the two products in the optimum bundle, but in itself it's not a solution because an infinite number of combinations of x and y can satisfy this equation. So to have a unique solution, we need an additional constraint which comes from the budget constraint, which is, so to have a unique this ensures an infinite number of solutions. To have a unique solution, we need a second equation, which is the budget constraint, and this condition can be built into the second equation. So finally we have this equation from the combination of the two constraints, and from this it follows that the optimum solution for product y is 250 and the optimum solution for x is 500 from this. And we can easily check that this solution satisfies the budget constraint. No surprise, it followed from the budget constraint and it satisfies the necessary conditions. No surprise, this is a consequence of the necessary conditions. So this is the complete solution to the most elementary optimization problem in economics ever. You can see the optimum solution is a two-element vector. So we found the optimum solution in the two-dimension Euclidean space. That's all. Is a more advanced example is the famous one-sector model of optimal growth. This is a problem we will extensively discuss in the course Recursive Economic Dynamics. Here we will just have a look at the strategy of solution. Production requires a single input. Let's go over the details. Production requires a single input, which can be regarded as the capital stock. So production takes capital. The outcome of production is a single input which can be consumed, or it can be saved as investment. So in any period, output can be consumed or invested. Production takes place according to a production function which has some basic characteristics, like it is strictly increasing, it is concave, and you can see there is a capital stock, X upper bar, which serves as the upper bound for production. In the second point, you can see the dynamics of the capital stock. So in any period, there is a certain amount of output from which society consumes, and the rest becomes capital stock next period. There is a utility function for the society, which has consumption as its argument, and the value function, the objective function, which we are going to maximize, is the sum of discounted utilities of the future. If the problem is sufficiently simple, we can solve it by a direct approach, which we will do in the next course. Note that a variant of this problem is the famous cake-eating problem, and if production technology is simple enough, and if the utility function is simply enough, we can take the so-called sequential approach. So we can solve the problem in the sequential form. If, like in this case, where the primitives of the problem is not too simple, we can use the famous Bellman equation. Okay, the Bellman equation is the core of all dynamic programming problems. So in the next slide, in the next part, we will have a look at this Bellman equation, which we will study in this course, and which we will study very extensively in recursive economic dynamics. What we are looking for is an infinite sequence interpreted as the capital stock. So we are looking for the optimum capital stock, capital dynamics for this economy, which, as we are working in discrete time, is an infinite sequence. So let's have a sketch of the solution of this one sector model of optimal growth in dynamic programming. In the next example, we will approach this problem, we will formulate this problem in an optimal control setting. So we will leave discrete time for continuous time. So let's go over the details of the problem which are key. First, this is the law of motion for the capital stock. In period t, the economy produces a certain amount of output, which a part of which is consumed, and the rest is invested and shows up as capital stock next period. The objective, so this was the law of motion. The objective is to maximize in terms, this is very important, the objective is to maximize utility in terms of a path for the capital stock. So this is an infinite sequence describing the capital stock. So we are looking for an infinite sequence which we interpret as the capital stock that maximizes the sum of discounted utilities. Beta is the discount factor, of which we assume that it falls between 0 and 1. And we have a utility function with the stated features, characteristics. So please note that this is what we have. This guy is the one we have in the bracket. So this is consumption in period t. All this implies that capital stock next period cannot be higher than output in period t, because we have two cases. We have two cases. When consumption is maximal, we have consumption as the total output in period t, which implies that capital stock next period is 0, which of course implies that capital stock next period is lower than output in period t. Intuitively, we feel that this cannot be an optimum solution, because it would mean that the economy consumes all its resources in period t, leaving nothing for the next period, for the next periods, because production takes capital stock. And if there is no capital stock left for the next period in any period, then consumption must be 0, because there is no capital stock in the economy. So intuitively, we can rule out this corner solution. If consumption is minimal, this is maximal, this is minimal, then it is 0, and from which it follows that capital stock next period equals output this period. So all in all, from these two cases, it follows that capital stock next period is lower than or equal to output in period t. So the givens are the utility function, which maps consumption into a real number, which measures the utility, and the production function, which maps a positive number into a positive real number into a positive real number. There is an initial capital stock labeled as x0, and we have the discount factor between 0 and 1. And we know from the required characteristics that that the utility function looks something like this. So there is so we have the diminishing marginal return case in this example. Okay, and let's have a look. Finally, let's have a look at the technology, the assumptions regarding technology. There is a maximum sustainable capital stock x upper bar. So this is the maximum level of capital stock. This is the maximum level of sustainable capital stock. This is a fixed point. So if capital stock is at this maximum level, the economy can sustain this level of capital stock until infinity. So this is a fixed point, which is strictly positive. If the capital stock is lower than, well, in general we can say, okay, so in general we can say that if the capital stock is lower than or equal to this particular level called x upper bar, then production cannot be higher than this level. In particular, this is a fixed point. I reiterate it for emphasis. In other cases, for capital stock which is strictly under this maximum level, then production is lower than this upper threshold. So in general, the production function looks like this. Okay, so this is x, and this is the production function, strictly increasing, concave. This is fx, and this is the level where we can find this maximum sustainable level of capital stock. Here, output equals the capital stock. And over this level, you can see at this level, the capital stock is higher. If the capital stock is higher than this upper threshold, then production is lower than the capital stock. Okay, when solving the problem appropriately, we need a state space. In which the state moves. So x moves in this closed interval. It cannot be negative. It can be 0, but it cannot be negative, and it cannot go beyond the maximum sustainable level of capital stock. If we start at this level, we must converge towards the maximum level. Okay, so in this case, the capital stock is on the decrease. All right, and the famous Bellman equation. Without any further ado, let's have a look at the Bellman equation of the problem. We will learn the rules of writing the Bellman equation. This is a value function. This is a functional equation, you can see. This is a functional equation because the unknown in this equation is a function. So we are looking for this value function that satisfies this functional equation. And all the work in dynamic programming takes checking whether certain assumptions are met. If these basic assumptions, which we will study in recursive economic dynamics, if these assumptions are met, then we have a solution which is unique and which has some very beneficial characteristics. You can see that the decision variable is y, capital stock next period. This is the decision variable. Capital stock next period. This is no surprise. If we have the capital stock this period as given, so if we have a certain capital stock, then capital stock next period depends only on consumption. So by taking the capital stock as a decision variable, we make the decision at the same time on consumption. So we treat capital stock next period as our decision variable, which includes the decision on consumption. So this is the Bellman equation, which we want to maximize with respect to capital stock next period. So we can proceed as if we were in an ordinary optimum problem. We want to maximize the Bellman equation. Okay, let me rewrite the Bellman equation. So we maximize the left-hand side of the Bellman equation with respect to capital stock next period. So all we need to do is to differentiate the Bellman equation with respect to the control, the decision variable y. So the first order condition is simply, we differentiate the utility function with respect to y, and we differentiate the unknown value function with respect to y, and in the maximum it must be 0, just like in the case of an ordinary first order condition, from which it follows that this is the first order condition. We have a problem here because the unknown in the Bellman equation is the value function, so we have no idea how it looks like. So we can use the envelope condition. The envelope condition, according to which if we differentiate the value function with respect to x, is like differentiating the left-hand side with respect to x. This is the envelope condition, which we use extensively in dynamic programming, and as it holds for any x, it applies to y too. And we can use this result in the first order condition. So finally, this is what we have. And let me double check. I think it's correct. This is Ljungqvist and Sargent's solution on let me have a look at, I think it is on page 112. This is in other form. This is the Euler equation of the problem. And you can see this is a first order difference equation that must be satisfied by the optimum capital stock. So we can use this Euler equation to find the optimum solution. Another method to find the optimum solution is a graphical approach, because we can draw a figure on the basis of this first order condition. If certain assumptions are met, then we can be certain that the value function, the first derivative of the value function looks like this, and we can be certain that you can see this is the left hand side, this is the right hand side, and this is the left hand side of the first order condition. So we can be certain under specific assumption that this is true, and the intersection shows the optimum solution to the problem. And this figure can be used. We will use this figure to characterize the policy function, which describes the reaction of the agent to any changes in the state, in the capital stock. So if a capital stock is higher, so instead of x, this is x prime, a higher capital stock, you can see that the optimum solution is also higher. This is just a sketch. So in this course, we will build up the algorithm or an algorithm to solve such a Bellman equation. And we devote the whole course entitled Recursive Economic Dynamics to solving such Bellman equations. This was just a sketch, just a teaser. We can formulate the same problem in optimal control theory, which means that we leave the vector space of infinite sequences. So we leave dynamic programming for the space of continuous functions and optimal control. What we seek is still an optimal investment plan, which is not an infinite sequence of capital stocks, but a continuous function on time. The main characteristics of the problem remain the same. We will have a look at the solution on the basis of the famous Cass-Koopmans model. So we will define the problem. We will identify the main characteristics of the problem, I will show you the Hamiltonian and the necessary conditions, and I will sketch how to proceed then.
So let's see a catch for the solution of the famous Cass-Koopmans growth model. The details are on the previous slide. Here, let's have a look at the most important aspects of the problem. The objective function is to maximize utility in terms of a consumption path, which is the same as maximizing utility in terms of a capital path, keeping in mind that capital stock next period is determined by consumption this period. We have two conditions to constrain the solution. We have two constraints. One is the change in the capital stock is given by output in period T, depreciation, and consumption. So you can see the change in the capital stock depends on consumption in period T and production according to the production function and the depreciation rate. So this is the first constraint, and the second constraint is a constraint to consumption which cannot be higher than output at time t. It's not entirely correct to say in period t, because here we have continuous time, so I would say consumption at time t cannot be higher than the output at time t. And the third constraint is the initial capital stock is given, which is given. So these are the basics of the problem, of the exercise. And now we will write the current value Hamiltonian. Later in this course, we will have a systematic overview of optimal control, even if the course recursive economic dynamics has nothing to do with the Hamiltonian, but the Hamiltonian must be in the toolkit of any modern economist. The current value Hamiltonian in this cookbook approach can simply be described with the utility as a sum of the utility which we maximize, the Lagrangian, this is the multiplier, and this is the law of motion for the state. So before identifying the Hamiltonian, we must specify that the capital stock is the state and consumption is the control variable. So on the basis of the capital stock, which is the state, the social planner chooses an optimal path for the control, which is consumption. So this is the Hamiltonian, this is utility, and actually this is what we call the current value co-state, which might be very useful and important in the solution. Most of the time it is. Okay, and now we have the necessary conditions. You can see that the Hamiltonian looks very similar to the Lagrangian function. These methods are closely related. The necessary conditions, we differentiate the Hamiltonian with respect to the control, the state, and the co-state. So, with respect to the control, which is consumption, this is the necessary condition. With respect to the state, which is K, we have this is the cookbook approach. So later we will discuss all the technical details. Okay, so this is the result of differentiating the Hamiltonian with respect to the state, where the Hamiltonian is the current value Hamiltonian. We could use the present value Hamiltonian. So later we will examine the differences. And with respect to the co-state, we have, actually this is the law of motion for the state. So we will have the law of motion for the state back. And in addition, the transversality condition conditions, if time approaches infinity, this must be true, and this must be true. So we have a set of necessary conditions where we stop now, but later we will see that this is the starting point for the exact solution of the problem, which requires the use of these necessary conditions to find a differential equation to describe the optimum solution to the problem, optimal capital stock, optimum consumption path. So we will work with differential equations. So the solution will be described with the differential equation or equations which are constrained and defined by these necessary conditions.
Our final example for the day is quite special. This is about a firm that maximizes its profit by planning a capital path, which is quite standard. It can be generalized into a whole economy, which can be interpreted as if it was a single firm, just we did in the previous two examples. What makes this example special is the strictly convex cost function, which penalizes too rapid capital adjustment. Later, we will see that this cost function is key in the formulation of this problem, because without such a convex investment cost function, immediate capital adjustment might be optimal. This is an extreme case. So the firm, using these mathematical methods, the firm finds its optimum capital stock. And given that without such a cost function, convex cost function, any adjustment speed can be chosen, it's optimal for the firm to approach the optimum level of capital stock in the shortest possible time, which is 0. So without such a convex cost function, the firm reaches its optimal level of capital stock in no time, immediately. But this is very unrealistic. So in more realistic cases, we can assume a strictly convex investment cost function to penalize too rapid capital adjustment. And as a result, capital adjustment will be staggered. Capital adjustment is slow, becomes slow. The first formulation of the problem is thanks to Eisner and Strotz in 1963, and this is one of the most widely cited papers in operation research and dynamic economics. For instance, all the early papers by Robert Lucas cites this study, this model by Eisner and Strotz. So in this model, we will sketch the solution. In this model, profit depends on capital stock alone. This seems to be a very harsh simplification, but even if we have multiple variable inputs, they can be optimized in terms of the capital stock, so they can be adjusted to the current level of the use of the capital stock. So at the end of the day, if the optimizing in terms of many variable inputs, these input uses can be adjusted on the basis of the capital stock. So at the end of the day, profit is dependent on the use of the capital stock only, because we can describe the use of the variable inputs as functions of the capital stock. We have a strictly convex investment cost function, which has two arguments. One is the change in the capital stock, and the other is time. The role of time might be neglected. In more complicated, in more complex cases, the role of time is in cases where costs are different in terms of time. So, for instance, if the firm starts an investment project later in time, then the investment costs of the same project might be lower. So it might make the firm interested in delaying the start of the project. Okay, but this is a complex case. In our case, the role of time will be neglected. So in our case, this convex cost function will have only one argument, the change of the capital stock, and in this sole variable, the cost function is strictly convex. Eisner and Strotz solved this problem in the calculus of variations, or variational calculus, which is a toolkit, which is a method which must be in the toolkit of the economist. So we will have a look at how they solve this problem. So all in all, in this introduction, we reviewed 3 key solution methods: dynamic programming, optimal control, and now calculus of variations.
So net profit of the firm is given, this is S, sorry, as the difference between revenues and costs. So this is net profit, based on which the firm seeks to find a time path. So the firm seeks to find a time path ST for the capital stock. So we move in the vector space of continuous functions to maximize this functional. So maximization takes place in terms of the path for capital stock. This is the usual discounting function. This is the profit function. So actually, what the firm is maximizing is the sum of its future profits, which can be wrapped up as a maximization problem in which we maximize in terms of the capital path. We are maximizing a function f with three variables: capital stock, the change in capital stock, and time. So this is the objective of the firm. To maximize this function, which can be wrapped up as a functional in which the unknown is a function, the optimum path for the capital stock ST. Okay, just for the sake of good order, the rate of interest is positive. Today, these problems we solve with the Hamiltonian we have just seen, but Eisner and Strotz solve it in the calculus of variations. So I'd like to show you how they solve this problem. Let's suppose sigma t is the solution. That maximizes JST. Okay, we don't know anything about sigma t. We just assume that this is the solution. It means that if we put this solution into the functional, then this cannot be lower than its value to any other possible solution, where mu t is some real function with 0 at the close end, where t is 0, and 0 at the far end, where t goes to infinity. If we take st is equal to this variation, we can say that the functional equation, takes this form. This is the first argument. The second argument is its change. Epsilon is a real parameter, so we have nothing to do with it when it comes to differentiating with respect to time, which we can wrap up as phi epsilon. Okay, so it's now that sigma t is the solution, the value of this functional equation depends on epsilon. Given that sigma t is the solution, it has a maximum where epsilon is 0. Where epsilon is 0. Because where epsilon is 0, st becomes sigma t, which is the solution, the unknown solution. By using this equation, we can say that the first order condition of maximizing the functional equation, this is what we are maximizing. Okay, so by using, let it be, yeah, okay. So by using this equation, we can say that the first order condition of maximizing the equation we are maximizing with respect to st is phi prime is 0, where epsilon is 0. Okay, so what I am talking about is that when maximizing this equation, we do the same when maximizing any function with respect to a variable. We need a first order condition, which we gain by differentiating the function, in this case the functional, with respect to the variable. So now we differentiate this functional with respect to the capital path st. So the basic principle is the same. If we maximize a functional in terms of a function, we differentiate the functional with respect to the unknown function, and hopefully we will find the solution. So this is what we are looking for. It means that we differentiate phi with respect to epsilon and take its value where epsilon is 0, which is the same as differentiating f with respect to epsilon and take it to be 0, which we can get by taking the total derivative of f here, the total derivative of f with respect to epsilon. Okay, by applying the chain rule in the integrand, we get phi prime epsilon fs mu fs dot mu dot dt, which we can decompose into two integrals. This is the one, and this is the second. okay, in which, okay, these are the partial derivatives, the first derivatives of f with respect to s and s dot. The second term on the right, I mean here, the second term on the right should be integrated by parts. And at the end of the day, we receive this solution. We are approaching the finish line. So this is what we get after integrating the second term on the right by parts. By definition, mu 0 is 0, and at the far end mu t is also 0, so this first term vanishes. We have nothing to do with that. So finally, we have this simplified equation, which is 0 to any real function mu t if and only if fs minus the time derivative of fs dot is 0. This is the Euler-Lagrange equation of the problem. This is something which you can use by memory. So if you define a problem in the calculus of variations, in any case, in the case of any problem, this is the Euler-Lagrange equation of the problem. This is a necessary condition that only ensures that phi has an extremum at epsilon, where epsilon is 0. So we need a second order condition by the negative second derivative of phi to ensure the existence of a maximum. This second order condition, where epsilon is 0, is simple by the second partial derivatives of fss mu square Yep. This must be negative to have a maximum. Okay, this where we were working with the second derivatives of f. So we have a second order condition to ensure the existence of a maximum where epsilon is 0, and finally Eisner and Strotz gets to these two equations. Which they derive from the first and second order conditions, Ps minus R Cs dot S dot times S dot dot plus C S dot T. Okay, this is 0, and their second equation is negative. So this must be negative. PSS, yes. S dot mu dot, okay. All right. And on this basis, they can characterize two characterize as closely as possible the optimum path for the capital stock. Most importantly, we want to check if its rate of change is strictly positive. So if the capital path is strictly increasing, and if the second derivative is negative, if it is to check if it is strictly concave. If these two conditions hold, and they do, trust me, the optimum capital path looks like this. And this is the pattern Eisner and Strotz find optimal. Okay, so this is the sketch of the solution, and later in this course we will study thoroughly these methods we surveyed today. That's all for the day.